Alright, so we're looking at Chapter 8, which deals with chemical composition. It's going to be a lot of topics in here. Most of it is definitely new to us. So we're going to take our time with it and get a good understanding of things. Alright, so what we're talking about in chemical composition is the actual makeup of your products and reactants and what they actually are. So in a reaction I have here, I have carbon and oxygen reacting to give just CO2. Well, the advantage of actually understanding what is all going on here, we really can look at things in a sense of something like this. If we knew exactly how many pounds or the mass of carbon that you're going to consume, you can actually use this technique to figure out exactly how much CO2 is going to go in. But what we're going to do at first is mostly just look at what CO2 is, how we know what that is. So a little bit more of the composition of the actual compound. Alright, so we need to be able to count it and relate it to those molecules, but we want to be able to count it by its mass. Alright, so let's talk about some masses, for instance. So carbon, for instance, the one we just had on there, does actually exist as 3 different isotopes. Now, they all behave chemically identical. Wouldn't matter if we have carbon-12, carbon-13, or carbon-14, our 3 main ones. In that previous experiment, they all react exactly the same. Matter of fact, even though carbon-14 there is actually radioactive, it makes no chemical difference in anything that uses carbon. It just happens to have 2 more neutrons than the average carbon. Alright, but when I look on the periodic table, I don't see carbon-12, carbon-13, carbon-14. It doesn't say anything at all about these isotopes. It gives the atomic mass, which is an average. And really what they did, they figured out the exact mass of that carbon-12 and multiplied it by its 98%, and the carbon-13 by its 1.1, and the carbon-14 by its 10 to the negative 11th percent, and the average carbon has a mass of around 12.011. Now, if you look on the periodic table I provide you, I actually have more digits than that. It says that on there it's 12.0107. And also, all of the atomic masses on the periodic table do have a variable number of digits. So they aren't just 3 decimal places. Some actually have 6 decimal places. So it varies based on how well we know it. But these averages that make up the atomic mass are figured out by looking at all the available isotopes. And some atoms have a lot of isotopes. Carbon's having 3 is probably around average. Most even numbered atoms on the periodic table, so even atomic number, have a lot of stable isotopes, and the odd number ones have less so. Okay, now when I'm dealing with a compound, something like carbon CH4, which is methane, if I wanted to figure out its molecular weight, we are looking at what it's made out of and how much they weigh. We're going to look at that here in just a second, but that compound is just made out of 1 carbon and 4 hydrogens. If I want to calculate the formula of a molecule, or calculate its formula mass is a better way of saying that, we actually do look up our individual atoms on the periodic table and we get their atomic weights. So H2SO4 only has those 3 atoms in it. There's 2 of these, there's 1 of those, and there's 4 of these. And then from the periodic table, you see that hydrogen has a mass of 1.008. Sulfur has a mass of 06. And oxygen has a mass of 16.0. So that entire molecule has a formula mass of, we can figure this out easily enough, so 4 times 16 plus 2 times 1.008 plus that 32.06, and I get 98.08. Now, technically, those 2 on, actually all 3 of these on the periodic table I provide you, I have a lot more digits, but really as long as you at least get 4 significant figures or 2 decimal places, you're going to have plenty of significant figures to actually get the formula mass. So we actually can round this, and it's safe enough of a number. But this mass, formula mass, actually has two acceptable units. I put grams, it should be grams per mole. The other unit that we could use is atomic mass units, which tells us that's the average mass of that entire molecule at the atomic scale. Or if we had a bunch of them, a mole's worth, that's how much it would weigh. Alright, that AMU in grams is kind of interesting because it was actually done in such a way that the AMU in grams per mole would actually have the same number in front of it. So what they did ages ago, we had defined our masses on the periodic table around carbon-12. Did that because it's a very common atom. Carbon-12 has 6 protons and 6 neutrons. So they added those together and decided that however this actually weighs, whatever its actual real mass is, they were just going to define it as having a mass of 12 AMUs. Just make it nice and simple. Alright, but that's an individual atom. Atoms are ridiculously small. We have a difficult time proving what their actual size is because they're so small. But, well, we have proved their size, but it was a challenge. What we wanted to do is get a much larger scale. So this grams versus AMUs, we want to be able to use the same thing and say that same number, but we want to change it to grams per mole. So our challenge was to know how many of these atoms. So this is atoms. This is a whole mole's worth of atoms, and we want to know how many that actually was. And that introduced this whole idea of Avogadro's number. So think of Avogadro's number as the chemist way of counting in groups. So we know from cooking, a dozen is 12, a pair is 2, a ream of paper is 500 sheets. Well, a mole, which is what we're going to use to count atoms by, is 6.022 times 10 to the 23rd atoms. So it's a huge number. And the reason it's not a nice even number or whole number or anything like that is because they wanted to have this ability right here to take 12 AMUs and turn it into 12 grams per mole, and we needed this to be a certain count. And it just so happened that count is 6.022 times 10 to the 23rd. So you have to have a lot of atoms to get a mole's worth. But that's fine. Atoms are tiny little things. We don't do much with individual atoms because they are so small. But even in a small amount of mass, even a few milligrams, there's a lot of atoms. Alright, so that mole number gets repeated a lot. 6.022 times 10 to the 23rd is just the conversion of moles into actual individual atoms for anything. Doesn't matter if it's a single atom like sulfur or gold. Doesn't matter if it's a molecule. That still is the number used. Alright, so if I give you a question like this, so if I ask you how many molecules are in 2.67 moles of carbon dioxide, turns out the moles of carbon dioxide is almost unnecessary because it turns out it doesn't matter what this is. The conversion is the same. A mole of anything is 6.022 times 10 to the 23rd of those guys. So I can actually write that conversion like that always, and this little thing is always going to work. Now how we put it on our calculator is a little bit tricky. So on my calculator here I put in 2.667, and then when I do this multiplication I can just do 6.022, and on this calculator I have this EE button. Most TIs have that, and that puts a capital but minimal, a small capital E. And now I put in that 23. That E is the times 10. But that actually does this math perfectly. And I made it go away before I actually read my number. 1.61 times 10 to the 24th. Alright. We could do that again. Same type of setup though. 4.5 moles of argon. We are just going to do that same type of thing. take our moles and then use our Avogadro's number to convert that to atoms. So 4.5 times 6.022 times 10 to the 23rd is 2.71. In this case it's C. Alright, ironically, we don't do this often, and that's mainly because atoms are so darn small. That's a tremendously huge number. And yet 4.5 moles isn't really that many moles of argon. That's a small amount, really. So actually counting by atoms it's not useless, it's just not something that's done commonly. Alright, now the atomic mass is something that's used a lot, and it does actually tell us a lot about the actual moles. But biggest reason we introduced that Avogadro's number right now is to complete this knowledge, so we can see that atomic mass, AMUs, goes to grams to mole and back and forth very easily. So they're interchangeable, and that's why on the periodic table there aren't really any units listed for the atomic weight. The atomic weight is either grams per mole or AMUs. Okay, so let's see if we can figure something like this out. So if I want to know the mass of moles of just neon atoms, the mass of a mole of neon atoms. So we want grams per mole. Well, that's just the units of our atomic mass. So to actually figure this out, I just look on the periodic table for neon, and I see that its atomic mass, or atomic weight, is 20.18 grams per mole. And just right next to that, 2 over of that, is oxygen, and the periodic table has it listed as 16.00 grams per mole. Alright, now, if it's a little bit more complex, we just have to add a little bit more of a step into it. So this is not asking us how much a mole's worth of sulfur atoms weigh. It wants to know how much 3.6 moles weigh. Alright, but what we're going to do is take that atomic weight we just looked at on the previous slide and turn that into an actual conversion factor. And I left off my units on my 3.6, so let me back that up. And 3.6 moles. So a conversion factor, I'm going to have moles here, so grams must be up there. And then I just look at the periodic table and see that the molecular atomic weight of sulfur is 32.06 grams per mole. So to get this answer, I really am just taking 3.6 and multiplying it by the 32. Three significant figures would be the 115. Alright, what are we going to do if it's actually a little bit more complex, like a molecule? So, a molecule of carbon dioxide has 1 carbon and 2 oxygens. We actually do get the mass of the actual molecule by using the atomic weights, or the molar mass, of the individual atoms. So since carbon dioxide is made out of carbons and oxygens, we really do just add those up. And that's how that came up, that 44.01. That 44.01 can also be used as a conversion factor, very similar to what we just did on that previous slide. So we could do something like this. Alright, so down here. So how many moles of each type of atom are present in 2.65 moles of CO2 molecules? Alright, so let's actually write this out so we can see what's going on. So 2.65 moles of CO2, and if I wanted to find out individual atoms, I would be using Avogadro's number, but this says moles of atoms. Alright, so it's still just leaving it in terms of moles. So in this case, we just want to say, well, for every CO2, there is just one carbon. And we could do another one of these. And we could say for every CO2, there are 2 oxygens. And it really is because that's what's in the formula. So the moles of carbons is the exact same number, 2.65. But this would be double it. 2.65 times 2. Now, the conversion factor would be the same even if we're going to atoms. We just have to add in Avogadro's number to actually get from moles into atoms. So that conversion factor could actually be talking about if we're dealing with moles or we are dealing with atoms or molecules. All right, so let's do some more examples of this. So let's calculate the number of atoms present in 3.75 grams of lead. All right, we got a couple things we have to do here because I actually can't turn grams directly into atoms because atoms were determined from moles. So I need to first turn my 3.752 grams into moles. I'm going to do that with the molecular weight. But if you notice, these are upside down compared to what we did before. So that's what I'm going to do. I'm just essentially going to flip it upside down. So I'm going to get my molecular weight of lead, which is 207.2, but I have it upside down so the units cancel. And now, since this would now be moles, I can convert moles into atoms with just Avogadro's number. And this, on my calculator, will look something like so. So 3.752 divided by 207.2 times 6.022 times 10 to the 23rd. And we get 1.09 times 10 to the 22nd. And this would be lead atoms. All right, next one. Calculate the number of molecules present in 52 grams of HClO2. All right, we got a couple things we have to do now because we're still going to go from grams to moles and then finally to molecules. But the molecular weight of HClO is something we'll actually need to calculate out. HClO2. Now this will be the same because we are going to be just converting this into atoms from our moles. The only thing that's different on this one is I need to figure out the molecular weight of the HClO so I can go in there. Get these molecular weights right off the periodic table. That's right where I put my calculator. So 2 times 16 plus 35.45 plus 1.008 gives me a molecular weight of 68.46. And so this full calculation, 52 divided by that 68.46 times 6.022 times 10 to the 23rd. And I get that this molecular weight, or this number of atoms, number of molecules, 4.57. What's that? 23rd, 23rd. And this would be not PB atoms, or not atoms, be HClO2 molecules. Alright, next one's going to be very similar to that previous one. we still will need to actually get the molecular weight of the P4O10. And rather than write it out, I'm just going to go right to my calculator. So phosphorus, has a weight of 30.97, and oxygen has a weight of 16.00. So P4O10 has a molecular weight of 283.88. And it does still want atoms, but it actually wants phosphorus atoms. So the very first thing I'm going to do is say that for every P4O10, I would have 4 phosphoruses. Right now that would actually be moles of phosphorus. I do want atoms, so a mole of anything is 6.022 times 10 to the 23rd. Let's see how big of a number this is. So 21.9 divided by 283.88 times 4 times 6.022 times 10 to the 23rd. Get 1.86 times 10 to the 23rd phosphorus atoms. All right. Far more common use of this is to deal with totally masses themselves and not actually look at the actual individual atoms. But something we might want to do is look at the percent composition of a particular atom in an entire molecule. So something like this. We have down at the bottom C2H5OH. That is ethanol. Component of gasoline, component of beer. But kind of a common molecule to a degree, even used in hand sanitizers now. But C2H5OH is a way of writing that out. Now if you notice, got the H's separated. This one's actually kind of written such a way that you could get an idea of how it's put together. And we do see that. There are certain times where the formula has all the atoms grouped together. So turns out ethanol could also be written as C2H6O. That's perfectly acceptable. And another way you can actually sometimes see ethanol drawn out is they're going to group the carbons with their individual hydrogens. So they're trying to say that this per carbon has 3 hydrogens off of it, which is connected to this carbon with 2 hydrogens off of it, which is connected to that oxygen with a single hydrogen. Looks something like this if I were to draw it as a stick figure. Well, none of those actually help us or say anything different yet, because they still have the exact same atoms in there. So when I get the molecular weight, I really would still do the same thing. I have 2 carbons, I have 6 hydrogens, and I have 1 oxygen. It doesn't matter how I write that, that's the actual number of atoms present. Even if I had a stick figure here, it's still 2 carbons and 6 hydrogens and 1 oxygen. So our molecular weight would be the same thing. Alright, so if I want to get the mass percent of, say, just the carbon in there, the very first thing I need to know is how much the entire molecule weighs. So that mass of the sample that shows here in this equation is that atomic weight, or that sum of the atomic weights. So ethanol, we get something like this. 2 times 12.01 plus 6 times 1.008 plus 16 gives us a formula weight of 46.07. Alright, Now, if I want to get the mass percent, we'll just do this one down here. It wants to know the percent of hydrogen in there. Now, even though there's a lot of hydrogens, hydrogens don't occupy a lot of mass. So to get the mass of the element, I am looking at the atomic weight of that element, and I am comparing it to the atomic weight of the entire molecule. But I can't just leave it like this, because it turns out there are actually 6 hydrogens in there. So all those hydrogens contribute to the weight of the hydrogens, so we have to use that number from our formula in this equation. And then we're going to turn this into percent by just multiplying it by 100. So the mass percent of hydrogen in ethanol looks something like this. 13.1%. And if we want to get the carbon percent, we're just going to change this to 2 times 12.01. And if we want to get the oxygen, we're just going to have 16 up here. But we could get the mass percent of any element in there, as long as we know that molecular formula. Alright, so let's actually do this with something like this. So what's the percent composition of carbon in vitamin C if I give you this formula? And I helped us out. I told us the molecular weight there. So what that means is we really can do something as simple as this. So if we want carbon, we know there are 6 carbons, so 6 times 12.01, the molecular weight of a single carbon, divided by 176.14, the molecular weight of vitamin C. Then we're going to multiply that by 100. And we get 40.91%. Now, if I gave you a question like right below there, how many grams of carbon are in 16.55 grams of vitamin C? We are just doing something like this. So the 16.55 is the molecular weight, or is the mass of vitamin C. So I am going to have that 116.4 down there, 176.14. Up here is just the carbon number. Or what we really could do, since we know our mass percent is 40.91, we really could just take that mass of 16.55 and multiply it by 0.44091. And that 6.77, well, 6.771 is the mass of carbon in vitamin C if we had 16.55 grams. All right. Weird thing is, we're going to use those percents we just saw, and we're going to kind of go backwards with them. We actually can use that to get the formulas of compounds. So, for instance, if I were to break down carbohydrates, so sugar, even starches, I would actually get the same mass percent of carbon to hydrogen and oxygen in there. Those formulas are obtainable simply by looking at those mass percents. But we have to analyze all the masses. So if I want to get the formula of the compounds, the very first thing I actually need to do is figure out which elements are actually present and how much of those atoms. So a carbohydrate is made out of carbons, hydrogens, and oxygen. Hydrate is H2O, carbons is carbon. Matter of fact, we know the exact ratio of them in carbohydrates, but we're not actually looking at that yet. That's first step is to figure out the elements. After that how much, that typically is like a mass percent. And it might look something like this when it's all done. Those mass percents might actually give us a ratio of carbons to hydrogens as 1:1. Benzene is the example I went to. Has for every 1 carbon there's 1 hydrogen. Its actual molecular formula, its actual number of actual atoms, there's 6 carbons and 6 hydrogens. But the mass percent that we just introduced on the previous slide would only tell us the ratio between the carbons and hydrogens. So we would actually end up with a formula of CH. But we can actually get from the empirical formula to the molecular formula if we just happen to know what the molecule's molecular weight is. So we need two things to get the actual molecular formula. All right, so let's break this down. Let's look at how we're going to go about getting this. All right, the composition, or those mass percents, can actually be used to give us an empirical formula. Empirical formula is just going to be the ratio of atoms to one another. That's this first one. Once you have that empirical formula, you can get the molecular formula as long as you have the molecular mass. So two types of pieces of data we would need. All right, so let's break it down. Let's look at let's pretend we have some percents, and I have some percents for acetone. It's 62% carbon, 10% hydrogen, 27% oxygen. And we're going to use that to get the empirical formula. So that's just the ratio of carbons to hydrogens and oxygens. Now, they should be nice whole numbers, and we're going to actually go through these techniques right here. So very first thing we're going to do is figure out how many grams are actually in there, and then convert those grams into moles. And then once we have the moles of carbon, moles of hydrogen, moles of oxygen, we look for the ratios between those. So we essentially divide by whichever one's the smallest. All right, so let's actually do that. We're going to do that right here. So here's those same numbers. So how do I get a mass out of a percent? We're just going to assume there's 100 grams, because then those percents turns right into masses. And it wouldn't matter if you assumed it was 1,000 grams or any number of grams. You just multiply that percent by it and go with it. All right, but it said on that previous slide, once we have our grams, the very first thing we're going to do is turn those into moles. So we're going to use the individual molecular weights for those individual atoms. And now I need to fire up my calculator and do a little bit of math here. 62 divided by 12.01 is 5.16. 10 divided by 1 is roughly 10, but I'm going to calculate it totally. 10.4 divided by 1.008 is 10.32. And 27.5 divided by 16. Now sometimes it's really easy to see the nice little ratios going on when you get to this step, but when it's not, we just take all these numbers and divide all of them by whichever value is the smallest. So that's definitely 1. But if I go up here and get that 5 and divide it by the 1, I get a nice whole number of 3.00. We are expecting these mostly to be whole numbers, so I'm actually going to round it off and just say it is a whole number. And then last one I have to do, 10 divided by the 1.7 is 6. So, having this information tells us that we have an empirical formula of acetone of 3 carbons to 6 hydrogens to 1 oxygen, C3H6O. Now that's not necessarily the molecular formula, it's just telling us the ratio of carbons to hydrogens and oxygens. The molecular formula is going to be a multiple of that, so it could be like C6H12O2, where we double everything, might triple them all, but the ratio is the same. It's always 3 carbons to 6 hydrogens to 1 oxygen. Alright, let's do another one, just so we get some practice. Vitamin C, one we just introduced. Matter of fact, a few slides ago, I gave you the molecular formula. Let's figure out what its empirical formula is. And then we'll back up and look at the actual molecular formula and see if it is any different. So I'm immediately converting those into masses. Just as I write them down, I'm just dropping the percent putting mass there. And then I'm putting here the molecular weight for each one of these. So 3.41. .54 and 3.41 again. Alright. Gonna see an issue here because I am dividing by the smallest. And that's definitely 1, and this is definitely 1, but that's a fraction, isn't it? So 4.5 divided by the 3.4 gives me 1.333. You notice how that's 3 repeating? Whenever we have 3's repeating or 0.5s, we're going to treat it like a fraction. We'll multiply all of these by 3 to get rid of that fraction. Gives us an empirical formula of C3H4O3. That doesn't look like a 3 at all. Alright, now back up a couple slides because we had vitamin C on there and I actually gave you a formula for it. And it says it's C6H8O6. Notice anything different here? Yeah, what we found, essentially half of everything. Because it's supposed to be 6 of these and 8 of these and 6 of these. So this empirical formula is half of what the actual molecular formula is. So it is a multiple of that, but that's typically what happens when you do an elemental analysis. You just get empirical formulas. If we did this for any carbohydrate, so table sugar or even starches, you would get an empirical formula of CH2O, which is actually where the name comes from. Carbohydrate, water, H2O. Alright. If I need to get the molecular formula, I need the molecular mass. Alright, here's how we go about using it. Let's pretend like we happen to know an empirical formula of a compound is just HO. But we also happen to know it has a molecular mass of 34.02. How can I use that to get the molecular formula? Well, I'm going to get a nice little whole number ratio. So what I need to do is figure out the mass of the empirical formula compounds. So that's a hydrogen and an oxygen. A single oxygen has a mass of 16.00. A single oxygen has a mass of, or a single hydrogen has a mass of 1.008. So HO has a mass of 17.008. And we're going to compare that to the molecular weight of whatever this compound is, of 34.02, and just do a little bit of math. 34.02 divided by that number I had up there, and I get 2. So whatever that molecule is that they're talking about, and they didn't even bother to name it, we do know it must be H2O2. To turn an empirical formula into a molecular formula, we just figure out what this little X is. In this case it was 2. And then we multiply both of our values, whatever those coefficients were. These were implied to be 1s. Multiply that by 2. Alright, so let's look at a bigger molecule. So, looking at a interesting one. Has a molecular weight of 110, and we actually know our masses of our carbon, hydrogen, and oxygen present. How will we go about turning that stuff into an actual molecular formula? Well, turns out steps 1, 2, and 3 are just determining the empirical formula. And then once you get the empirical formula, you convert to the molecular formula just like we did on that previous slide. So let's do all that. All right, so I have 16.36 grams of carbon. I have 1.38 grams of hydrogen, and I have 7.265 grams of oxygen. My very first step, convert those all into moles. That is 1.362. That is 1.369. And last one, 7.265 divided by 16 is 0.454. And we're going to divide all these by the smallest. And within reason, I'm going to say these two are the same number, so I just need to do one of those. Take that and divide it by that, and I get a nice number of 3. So I have an empirical formula of C3H3O. Alright, now we got to determine if that is the empirical, if that is the molecular formula. So I'm going to figure out how much that would weigh. So I have 3 carbons. I have 3 hydrogens. And I have a single oxygen. Mass of that is 55.05. And we're going to compare that to the 110.12. And don't really need to do this math. That's 2, but I'm going to type it in anyway. So, hydroquinone actually has a molecular formula of C6H6O2. Just double everything. Alright, got several practice problems for this. Give it a try, see how it works out. Send me any questions.